Hello and welcome back to Calculus 1. We are almost done with chapter 7. Tonight's lecture on L'Hopital's rule. So, disclaimer first. It's not L'Hopital's rule, it's Bernoulli's rule. So, in the past, L'Hopital was this rich guy who has a lot of interest. He had a lot of interest in mathematics, and he was paying Bernoulli to be his tutor. Now, in old days, there was no YouTube, internet, or anything like that. Books were non-existent or scarce. So, the way to learn math is to actually pay people who did the research in math and knew math in universities, because the knowledge was not readily available, and he was paying Bernoulli to teach him calculus and all of these things. And Bernoulli kept sending papers. So when L'Hopital learned enough, he dared to write the first ever calculus textbook. And in that textbook, the rule that we are going to see tonight was published for a very first time ever. And people seeing that, right, because when the calculus book came out, all of the people that were interested in calculus and those who knew some of the calculus wanted the book, obviously. And they seen this rule. They've never seen it before, and they thought it was his rule, and they started calling it L'Hopital's rule because they were unfamiliar with the fact that that was actually Bernoulli's rule. So that's a little piece of history. The reason why it's still called L'Hopital's rule is because it's honoring the L'Hopital for writing first ever calculus book, opening the era of publishers and things, right? So what is this rule? This rule is going to help you take the limits when it's tough. It works only in certain situations. In order for the rule to work, we must have something that is called the indeterminate form. And you get the indeterminate form when you plug in, you have the first way to solve limits is to plug in value, right? So if you get 0 over 0 or infinity over the infinity, that's called indeterminate form, and this is where the rule kicks in. So, in order to use the rule, we must have indeterminate form. Zero divided by 0 or infinity divided by infinity. Example would be one problem that you had to memorize. So we have limit of sine x divided by x as x goes to 0. So as you plug in 0, because that's the first way to solve these problems, when you plug in 0, you get 0 over 0. And then, because you have 0 over 0, that is indeterminate form, and we can use the rule. So that's that. How do we achieve this? Well, what is the rule? Sorry, what is the L'Hopital's rule? L'Hopital's rule states that if you have indeterminate form, the problem that you are solving is equivalent to the problem that is quotient of the derivatives. That's the L'Hopital's rule. So, rule states the same. If we have 0 over 0 or infinity over infinity, then limit of f of x divided by g of x, as x is going to either number or infinity or whatever, so x goes to, let's say, a, we put the L apostrophe H over the equal sign, and we write limit f prime of x divided by g prime of x as x goes to a. So that's that. It is very important to understand that these two problems are not the same, but they have the same answer. All right? So two problems are going to have different functions. This is not a quotient rule. It's just two separate derivatives. We know that's not the way to find the derivative of quotient. So this has nothing to do with anything we did so far. It's not a quotient rule, and the functions are not going to be the same. However, the theorem guarantees that they will have the same answer as the limit. So now if we are to solve the problem above, limit x goes to 0 of sine x over x, we see that we have 0 over 0, which I indicate with these red zeros on top and the bottom. So that's 0 over 0. And then I can put L apostrophe H on the equal sign, because I'm saying that the next problem has the equivalent solution. And now I take independent derivatives. Derivative of sine x is? Very good. And derivative of x is? 1. Now when you try to plug in value, cosine of 0 is 1. You get 1 over 1, which is 1. And this is something that you were supposed to memorize before, but now you know how and why it is what it is. Bueno? And believe it or not, the lecture is over. However, I told you that this is extremely long section. So this is it for the rule. If there is infinity over infinity, or 0 over 0, you take independent derivatives. If you run into another situation, 0 over 0, infinity over infinity, you do another derivative of that. Eventually you will get out of that loop, and you will be able to compute the limit. So what makes this lecture long? Well, there are modifications that this can be used for. We have situation of infinity times 0. Infinity minus infinity, 1 raised to infinity, 0 raised to 0, and all of these other cases where this kicks in to help us solve it, which makes this section very long. But the rule and the core of the whole thing, that's that. There's nothing else to it. We can do another example if you want with infinities, but the core is done. So here's another example. Say you have limit x goes to infinity of x squared plus 3x minus 6 divided by 2x squared plus 1. Right, so this is the problem. So now you're looking at this and you say, all right, the first way to solve the problems is to plug in the value. First of all, you should know the answer of this question just by looking at the problem. What is it? What's the answer for this limit? 1/2. The answer is 1/2. You have the same exponents. And the ratio of front coefficients is 1 and 2, so 1 divided by 2 is 1/2. So what are we doing here? To solve that, sure, you remember the way, divide everywhere by x squared, right? Or the shortcut method is to remember the relation of the powers. Now we're learning the third method. This says plug in infinity, what do you get? And you actually do get infinity over infinity, because you have infinity plus infinity minus 6. Over here on the bottom, infinity plus 1. So that's all infinities. So if you have indeterminate form, infinity over infinity, you can do the L'Hopital's rule. So you will put L'H on the equal sign, and you will find independent derivatives of numerator and denominator. So still copy the limit. We haven't done anything yet with the limit. So limit x goes to infinity, and now derivative on top is 2x plus 3, and derivative at the bottom is 4x. Now you plug in infinity, you get another infinity over infinity case. So that means another L'Hopital rule, and we get the limit x goes to infinity of 2 divided by 4. Well, that's 1/2. There are no more x's to plug this infinity for the limit, so we can just ignore it. So this is now the third way to solve the same type of problem we learned in chapter 1 or in pre-calc, right? So ratio of front coefficients if the powers are the same. If top is bigger, it's does not exist, and if bottom is bigger, it's 0. But then again, you can just look at the limit. So that's the basic idea for L'Hopital's rule. And now we start making it interesting, in quotation. Interesting. So we want to see other cases, and we do have a case which is 0 times infinity. So case 0 times infinity. So in order for us to work on this case, we first have to just make peace with one of these facts. F of x is equal to 1 over 1 over f of x. We will need this manipulation. This manipulation allows you to change a function into a quotient, because remember, it's 0 over 0, infinity over infinity, that we are trying to work on. So now that you have this situation, we can just go on and solve the limit problems. So first of all, just to make it clear one more time, L'Hopital's rule is only the definition we have in the beginning, and it only applies to 0 over 0 and infinity over infinity. And the lecture is over, okay, for L'Hopital's rule. But within the same lecture, there are all these other cases where L'Hopital's rule is useful. And from this point on, in this lecture, all we are learning are tricks, algebraic manipulations to transform what we have into form that L'Hopital rule applies. So this is not L'Hopital's rule, what you're looking here, right? We are reserving L'Hopital's rule for 0 over 0, infinity over infinity. That's 0 times infinity, so that's not it. We have to find a way to transform the problem into. Hence, we are using this algebraic trick, which will change stuff around so that we can finally do this. So let's take a look at some examples. Now, obviously, the examples that are worked out in a book, you can read those. I will pick some up from the years.
When you have like a negative infinity, where it's like the limit to negative infinity, is it like the same as the regular infinity that you deal with?
Yes. There is a concept in mathematics that shows that those two infinities are actually the same thing, but yeah.
Different?
No.
Oh, just like the same.
It's dull. So let's take a look at a problem. We start with a vanilla problem over here. Limit x cosecant x as x goes to 0. Great. Now you want to know whether this is 0 times infinity or not, right? So what we do is we first figure out what is the cosecant of 0. Cosecant of 0 is 1 over sine of 0, which gives you 1 over 0. So it seems that that piece is infinity. You can also draw the graph. If you draw the graph for sine, and you put vertical asymptotes wherever sine goes through the x-axis, and then just invert these to draw the cosecant graph, what do you see for cosecant at 0? You see infinity, right? So we know that the first part is 0 and the second part is infinity. So we have 0 times infinity. The trick to solve 0 times infinity problems is to use this algebraic manipulation, which I put up. So function is equal to 1 divided by 1 over the function. And what I'm going to do is I'm going to flip the cosecant using that function. So now, I am not placing L apostrophe H. I just write equal because this is just good old algebra. And this algebra is x divided by 1 over cosecant x. So if you are observing what's happening here, this one over here is the f, right? I took that one to be f. So all I need to do is to put it as 1 over 1 over f. 1 over 1 over f. I mean, there is a 1 over here, times 1, right? This x was already over here, right? That x is already up there. Now, clean up the algebra. So limit x goes to 0. And I have x divided. Does anyone know what 1 over cosecant is? Very good. Excellent. So we have now a new problem. So every time you come up with a new problem, you immediately test by plugging in. And now when you put in 0, you get 0 over 0. And this is where L'Hopital gets excited. Because now we can use the rule. We have 0 over 0, which means, yay, independent derivatives. So limit x goes to 0. Derivative of 0 on top is 1, and derivative of sine x on the bottom is cosine x. So the whole thing is 1. When you plug in 0 for cosine, cosine of 0 is 1. And you have 1 divided by 1, which is 1. So that means that the limit of x cosecant x is equal to 1. Now there are many ways in which you can check this. You can type the entire problem in Mathematica and get the answer, sure. But you can also just graph. And look what a graph does at 0. Because we are approaching 0 from left and right. So I want to know what's happening in that case. So just graphing it is sufficient to verify your that everything is good. So x times cosecant x. And if you pay attention over here, you see that it goes through 1. So the limit at 0 is 1. So let's do another one of these examples. With each step it becomes worse. So this is important for the foundation to see this problem. So let's try one more. $49. Limit of pi over 2 minus x times secant x as x goes to pi over 2 from the left, so minus. So you know the drill. Test, if you get 0 times infinity, take the cosine, flip it, use the identity.
And we have forms in multiple variables. And you can bring the family in instead of bring the back.
Okay. I got it.
Oh, yeah. Okay. And I have more forms and stuff.
Okay, so we are going to do the same deal. Pi over 2 minus pi over 2 is 0. So the first parenthesis is 0. Now the second parenthesis, secant of pi over 2. Now this is a skill that you have to have from your pre-calculus 2 course. Secant of pi over 2 is 1 over cosine of pi over 2, which is again 1 over 0 as a calculation, right? That brings you infinity. Or if you want to draw the secant graph, you can quickly draw the cosine graph, and then at every 0 strike the vertical asymptotes and just invert all the cups and then get rid of the cosine graph, and this is your secant graph. So pi over 2 from the left, pi over 2 is here, and when you approach it from the left, you see it goes to positive infinity. It doesn't matter whether it goes to positive or negative infinity, the rule works the same for both. So we have 0 times infinity, and for 0 times infinity, what we do is we take, we do the rule again, and we do it on the trig function. So again, we are not putting the L'Hopital yet because we are just doing algebraic manipulations at the time. So I'm going to have, I don't need parentheses, pi over 2 minus x divided by 1 over secant x, which is limit x goes to pi over 2 minus, and now what you have is pi over 2, the derivative of that is, sorry, pi over 2 minus x stays the same. And what's 1 over secant? Cosine x. Nice. So now you plug your values. Pi over 2 minus pi over 2 is 0. So we have 0 on the top. And cosine of pi over 2 is also 0. So we have 0 on the bottom. And there's our indeterminate form. So now we can unleash L'Hopital over here. So now that we have 0 over 0, L'Hopital's rule kicks in. We have limit x goes to pi over 2 minus. When you take derivative on top, you get negative 1, right? Derivative of pi over 2 is 0. Derivative of negative x is negative 1. And then derivative of cosine is negative sine. So that is, these negatives now cancel. When you plug in pi over 2, you get 1 over 1, which is 1. Negatives canceled. Make sense? Anyone? Yes? Until you get home and do the homework, right? Then nothing makes sense. I was like, oh yeah, it's so easy. Ready for the next case? Infinity minus infinity. Wouldn't it be nice if we just could say infinity minus infinity equals 0 and move on? Right? It would be amazing. But no. Infinity minus infinity could be 0, could be 1/3, could be 3/4, could be anything. I can actually make infinity minus infinity to subtract into any value I want. Just depends which functions I get to use. So this is where calculus goes a little bit abstract. So to start these problems, start a new notebook, I guess. These are a little bit lengthy. There's a lot of algebraic manipulation. The question is, before you start doing anything here, how do you get from subtraction into a division? Right? How do you... Magic, yes. So we will have to become magicians to actually go from subtraction into this. So here's what's happening, guys. We start with subtraction. And then that, by use of factoring, will be turned into multiplication, which would be 0 times infinity. And then that one needs to change into one of the two L'Hopital forms by use of 1 over 1 over f. So this is like a roadmap to solve this problem. And then we can do L'Hopital and win at the end. So that's the map for infinity minus infinity. So for these problems, they have very interesting problems in examples in a book, and then they have very lousy examples. So let's work on one example from the book, and then one from the homework. No coffee. So, the problem is to evaluate the limit x goes to infinity for x minus square root of x squared minus 3x. They only have 4 of these examples in the back, so I'll solve one of the homework as well. Alright, so this is the problem. I hope you see that there is infinity minus infinity there, because you have infinity under the square root. The square root of infinity is infinity, and plug in infinity for x in the beginning of the problem, so you have infinity minus infinity. So this is the case that we are trying to study. Now, what I said is you have to use factoring to turn subtraction into multiplication. Well, great. How are we going to do that when I can't factor x? Right, the square root doesn't have x in front of the square root to be factored. So we have to make one. So the goal is to have an x over here. and then I can factor that x along with the other x, and that will create multiplication, and then change multiplication into division. But I don't have x over here. So the way I can get an x over there is if I have a x squared factored inside that will escape the square root and become single x in front. So now I need to have x squared inside. But then I see this term, which doesn't have an x squared, so we have to fix that. So that's the backwards kind of thinking that helps in getting these problems done. So limit goes to infinity of x minus, and now what I have over here is x squared minus, and I'm going to multiply this term with x over x. So this will now become 3x squared over x. The next step is to factor out.
Just multiply it by x over x.
Yes, multiply it by x over x to get x squared. That's the goal. So now I can factor out that x squared, and what's left is 1 over 3 over x. So when I factor out x squared, what's left is 1 minus 3 over x. And now this x squared goes outside of the square root and it goes out as a single x. So limit x goes to infinity, and now I have x minus x times the square root of 1 over 3x. Alright, so we are about halfway done with the transformation. Now we get to factor the x, and there is finally our prize on doing all of this. X times 1 minus the square root of 1 over 3 over x. That's the line. Try it, and you will see that you have infinity times 0. You say real quick. I can't because we gotta move. So now, if you plug in infinity, you get infinity over here. 3 divided by infinity is 0. Square root of 1 is 1. 1 minus 1 is 0. So infinity times 0. This is the time when you use the 1 over 1 over f. So limit x goes to infinity, and we have 1 minus the square root of 1 minus 3 over x divided by 1 over x. So I took that x and I forced it into the denominator, and when it goes into the denominator it becomes 1 over x. So that's the 1 over f rule. When you check infinity now, you have 0 over 0. Check it quickly. You need to be able to make those mental calculations. So 3 over x is 3 over infinity, that's 0. So the only thing that is left under the root is 1. Square root of 1 is 1, so 1 minus 1 is 0 for the top. And then 1 divided by infinity is 0. So that's also 0, and we have 0 over 0. Now, at this point, we can do L'Hopital because we have indeterminate form 0 over 0. So now this is where L'Hopital kicks in. and you are taking two independent derivatives of this stuff. Now, the one on the bottom is easy. That's just negative 1 over x squared. Right, so negative 1 over x squared here. And on the top, the derivative of 1 is 0. Then we have that minus sign. I'll put that as negative 1 times. And now we have to take derivative of the square root, which is the chain rule. So that's going to be 1/2 1 minus 3 over x to the negative 1/2, right, as a derivative, and then times the derivative of the inside. And the derivative of the inside is, derivative of 1 is 0, derivative of negative 3 over x is positive 3 over x squared, because negative and negative canceled. We still have the limit, but we at least done the L'Hopital part. And now what can I do? Well, the first order of business for me is to cancel x squares. That's the first order. And then I can also cancel the 1, the two negative ones. So negative is canceled with a negative, and the negative 1 is gone from the top. So what's left? Well, there's nothing in the denominator left anymore. All you have is what you have on, oh no, negative 1/2. So you do have the denominator. You have 1 minus 3 over x, the square root. And then you have 3. And you have 2 over here. All right, good. Let's chase this together. Negative 1 and negative 1 cancel. 1 over x squared and 1 over x squared cancel. So we are left only with this, with a 3. So 3 goes here, becomes 3/2. That's 3/2. And the parenthesis over here is raised to negative 1/2 exponent, which means it should go in the denominator. And it's 1/2, so it's a square root. Now try the infinity. And what you just witnessed is that infinity minus infinity gives you 3/2 as the answer. Now, as I said before, I can make this answer anything I want. Anything. I can make this answer anything I want, because what you get over here at the end depends on the functions we started with. So you see this 3x at the end? I can change that into 4x, and then the answer will be 2. Right? Because that 3 that propagated as a 3 at the end, the 4 will propagate in the same way and give me 4. 4 divided by 2 is 2. So we can make anything. That could be a cool challenge problem on the test. Write the problem infinity minus infinity, so its solution is 2. Right? As a follow-up to a problem, it's already done. What's left are 3 exponential forms. We end at 7:35, so we have plenty of time. We have 3 exponential forms, and all of these exponential forms are solved the same way. We ln both sides. Remember the logarithmic differentiation? Set y equals everything, ln both sides. Well, now these functions are going to have the nasty exponents, and when you ln both sides, that exponent goes in front and creates 0 time infinity situation, and then again flip things, and you go from there. So let's take a look at the last 3 cases. So we have 1 raised to infinity, 0 raised to 0, and infinity raised to 0 cases. I hope you see that, right? You would want so much to use common sense of these, but it doesn't work. You can't use common sense for these. What is 0 raised to any power? 0 squared is 0. 0 cubed? What is 0 cubed? It's 0 times 0 times 0. Right? So 0 raised to any power, common sense should say, it's 0. Now how about any number raised to the 0? 1. 2 raised to 0 is 1. 3 raised to 0 is 1. 1/2 raised to 0 is 1. Anything that you raise to 0 is 1. So now, this one is pushing for answer to be 0 all the time, and this one is pushing for the answer to be 1 all the time. You see that? So they're pulling in two different ways. There are going to be some problems when the answer is 0. There are some problems where the answer is 1, but then there are some answers where it's e squared or 7. Right? So you actually have to solve these. The biggest one is the first one. How hard is 1 times 1 times 1 times 1 times 1? But you keep giving answers. Yeah, 1, 1, 1, 1, 1, 1. Every time I say times 1, 1, but now when you solve a problem and you see that the answer is e squared, you go, what? And yeah, it is. Your compounding interest works on that one. Right there. That's the continuous compounding, which gives you the maximum possible return on your investment. If you are investing money, and obviously if you're borrowing money, it gives you the maximum amount of money you have to pay, right, to repay the loan. So let's take a look at these cases. Let's start with some vanilla case, something that it's not. Well, let's do x to the, 3x, whatever. So limit x to the 3x as x goes from 0 plus. As I said, you have to create function, leave enough room to squeeze in ln. So y equals, leave some space, limit x to the 3x as x goes to 0 plus. And now you hit ln the both sides. The ln and limit can swap their places because ln is increasing function and other reasons in math. So swap the places for the limit, which now goes there. And now you have ln of x 3 to the x. The rule for logs says that ln x to the p is p ln x. So this exponent of 3x is going to drop in front of ln. So ln y is the limit, x goes to 0 plus, and now we have 3x times ln x. Now as you are approaching 0 from the right, the 3x term is 0, and ln x of 0 is negative infinity. So you have your 0 to infinity case. So now we'll say use 1 over f to turn that product into division so that we can use L'Hopital's rule. So ln y is equal to, and now which one do you want to flip? Hopefully 3x. So we have ln x over 1 over 3x. So the next line, ln y is equal to, oh wait, hold on, we have to check if the limit, so we have 0, we get infinity, 1 divided by 0, we get infinity. I don't care that the top one is negative and the bottom one is positive, no one cares about that. So we can do the L'Hopital's rule and do the L'Hopital of ln and 1 over 3x. So what do I get? I get limit x goes to 0 plus. The derivative of ln x is? Very good. And then derivative of the denominator is negative 1 over 3x squared, yeah. Right? So now we're going to just deal with the double fraction. So 2 that are far apart multiply on top, and 2 that are close by multiply on the bottom. And we see that this cancels to negative 3x. So ln y is equal to oh, that's the problem. I didn't copy the limit. See, something is not good. Okay. So these guys cancel. There is still a limit over here of negative 3x. So what do I get? I get a 0. Because x goes to 0, and when I plug in 0 in there, I get 0. I just have to quickly check all of this to make sure everything is good. So now, to find y, which, by the way, represents your entire problem, including the limit, you e both sides, and when you e both sides, y is equal to 1. Sorry, so if y equals to 1, that translates into limit, and this is the whole problem. X to the 3x equals to 1. Not as bad as the previous ones, right? I mean, I filled in a lot of steps that I would not write if I'm solving the problem for whatever reason. But it's important to see all the steps once, at least once. Let's do another example. Limit sine raised to the tangent. So limit sine theta raised to the tangent theta. Same steps. Oh, that goes to 0. X goes to 0. Let's see what you can do on your own for It's okay to talk to people. Say bye.
Like theta.
Sine theta raised to the tangent theta.
This is really like theta goes to 0.
Oh, yes. Thank you. Yeah, it's not x goes to 0, it's theta goes to 0. It's not official break. This is when you do the problems. Break is after. Okay, let's take a look at this problem together. So we are going to assign y equals, leave some space, limit theta goes to 0 of sine theta to tangent theta. We are going to add in the ln on both sides. And now we're going to swap the order of ln and limit and also peel off the tangent from the top in one shot. So ln y is equal to limit theta goes to 0. And now I have tangent theta times ln of sine theta. So the exponent went in front of ln. When I plug in 0, tangent of 0 is 0, sine of 0 is 0, but ln of 0 is negative infinity, so this is the 0 times infinity case. Also, and now we have the 1 over tangent situation. So ln y is limit theta goes to 0. Ln of sine theta stays, and this becomes 1 over tangent theta. You had 1 over sine. One over tangent is cotangent. So ln y is the limit theta goes to 0 of ln of sine theta divided by the cotangent theta. And this is going to be infinity over infinity, because cotangent graph has the vertical asymptote at pi, and it goes like this. So you see it's a positive infinity as the limit goes to 0. So I have infinity over infinity. I mean negative infinity over infinity, doesn't matter. Infinity is infinity. Positive or negative, in this case. So now I get to take the derivatives independently, and this is where we are going to put L'Hopital, because now we are taking derivatives. Derivatives of ln. Copy the argument as is and put its derivative on top. And derivative of cotangent is? Very good. So you can put that cosecant as 1 over sine squared and deal with the algebra before you do any calculations. Just clean it up a little bit. So you have cosine theta over sine theta divided by negative 1 over sine squared theta. You see that one of the signs cancels. So ln y is equal to limit theta goes to 0 of negative sine times cosine. Sine theta, cosine theta. And when you plug in 0, it ends up being 0. Because sine of 0 is 0, and cosine of 0 is 1. 0 times 1 is 0 at the end. So we got that ln y is 0. Again, we e both sides. And when we e both sides, y is equal to e to the 0, which is 1. Which implies that our problem, which is the limit of tangent raised to sine raised to tangent. So limit of sine theta raised to tangent theta as theta going to 0 is equal to 1, because the entire problem was labeled as y. If you go back to the first step, if you ignore the red ln's, the entire problem is set to y. So if y is 1, then the entire problem over there is equal to 1. And that's the answer. Just a whole bunch of algebra. And then some derivatives, right? Now, it's very systematic. It's very systematic, so if you do a lot of these problems, it should sink in quickly. The bag of tricks over here is finite. So we start with learning that 0 over 0 and infinity over infinity is called the indeterminate form, and L'Hopital's rule works only when you do this. Now, we have cases 0 times infinity, infinity minus infinity, all of the exponential cases like 1 to infinity, 0 to 0, and so on. And all of those you have to use algebraic manipulations to first bring them to indeterminate form and then unleash L'Hopital's rule, right, with the separate derivatives to do this. And then that takes care of the problem. Are you ever going to see this again after Calc 1? Well, if Calc 1 is the last class you're taking, yes. However, if you're going to Calc 2, you have the entire chapter to utilize this. Actually, and then more sections here and there. Calc 3, differential equations. So this is one of the main methods of taking derivatives, taking limits later on in your math courses. So if you are pushing past Calc 1, you absolutely must know this, otherwise you are doomed. So this is one of the very important sections. We'll take a 5-minute break. When we come back, 4.9, antiderivatives, also known as integrals. Ciao.